Now let us look at method 2 of accessing hardware, and we spoke about it. It is through structures. So this is taking the same set of registers that we saw, that is the SysTick registers. We again have 4 registers, same 4 registers: control, load, value, and calibration, as you can see. So these are the 4 registers. Say the control register at an offset 0, and then the load register at an offset 4, and the value register at an offset 8, and the calibration register at an offset 12. Okay. So it's the same set of registers. We are going to apply a different method to. Now what we are going to do here is this is another very it's an intelligent way of mapping this entire memory region. That is, declare a structure with, say, like this type def. So however you declare it, declare the structure and do a volatile and then all these values. Okay, so these are 32-bit values inside the structure, and then type def struct, and this is the structure name. Now what happens here is, so far we have not done anything. But if you look at the structure, if this is your SysTick memory location that we saw in the programmer's manual, and then we declare a structure called SysTick type, suppose. Okay, and this means from the lowest address to the highest address. Okay. So the first one is at an offset 0 and 4 and so on. So your structure will be, so if you turn the structure over on its head, so we'll have type def struct, and then probably you'll have this, and then your CTRL value maps to here, load value maps here, and then value, that is counter value, maps here, and then calibration value maps here. Okay, so this structure, if you turn the structure on its head, and this is the increasing memory location, say from E000, or you can invert this memory location and go from bottom to top, but we generally follow the convention of go from top to bottom. We generally follow the convention of bottom to top. So the structure elements that you see here, okay, will represent a memory space, okay, which will have the same kind of distribution of variables across the memory locations. So this will be at the 0th offset, this will be at the 4th, and this will be at the 8th, and this will be at the 12th offset. Okay, if these are all word aligned. Again, we said that there are some issues where the compiler is going to pad the structure for certain purposes and so on. So assuming that this structure is not padded, this will not be padded. Okay, if so, now generally when you declare a structure, you will create some address space. Okay, so suppose you declare this structure called SysTick type. So from your usual general knowledge of structures, so SysTick type, and then you probably name a structure here. Once you name a structure, some addresses will be assigned. Okay, so this memory will be assigned to that particular structure, and then you probably declare a structure pointer and then do an ampersand of that particular structure that you declared, and then you access that structure with arrows, right? So this is a standard way of accessing structure pointers. Here the structure pointers are used in a different way. That is, you declare a structure pointer. So you declare a structure pointer, but the structure pointer need not always point to a structure. Okay, so the structure pointer that you have, pointer, can point anywhere. The structure pointer can point to any memory location. The only thing that you need to do is to cast the location to the structure type. Okay, so what does that mean? Any memory location casts that to the structure type. So for example, if we have this particular structure, say we have this particular structure which is cystic type. Now we have the, say, the memory location E00E010. That's the memory location, right? I keep forgetting. Yes, E00E010. So if you make this structure point to this memory location, this is not a structure, mind it. This is just a memory location with, it goes up 1418, whatever you saw. But we are assigning that structure pointer to a memory location and casting it to be this structure type, that is cystic type. That's all. Once you do that, once that pointer is cast to this structure pointer and you cast it to this structure type, the structure pointer does not need to, it is not the structure pointer's business to really know what it is pointing to. It may be pointing to anything, okay, but it will look at it like a structure. So I repeat, it may be pointing to anything, but it will look at that memory area, it will look at that memory space like a structure. So it will look at it like a structure. And that's the beauty of this way of accessing memory. So you have this memory here, and you just assign this to the structure pointer, and once you assign it to the structure pointer, you typecast this particular memory location into the structure type. In method 1 we didn't do that. We just typecast it as whatever we wanted. For example, like volatile unsigned int or volatile unsigned half word or char or whatever. Here we are actually declaring a structure, and we are assigning the pointer or assigning this memory location to that structure pointer, and in a way fooling that structure pointer to believe that it is pointing to a structure. Okay, so that is all we are doing. So we'll cheat a little bit and we'll copy the code from here, because this is a working code. So we'll not copy this line yet. Okay, so we'll do it in the conventional way. Let's copy this one and we'll put it in our code. So I'll erase this part. If you want this diagram, you can just go back and see the video, because otherwise this will not be able to comprehend. So now what we do is whatever type defs that we have here will be necessary for explaining padding. So I just keep it here, and we'll add that structure declaration that we saw here. Okay. So this is the structure, and this is the structure declaration here, cystic type, and like so. Now we'll keep this part of the code here because we will make changes to this. So we'll follow the same exercise of writing some values in the registers, but this time we are going to do it in a different fashion. So we'll delete all of this. Okay, and this one too, and we will write the code in a different way. So what do we need to do? We need to declare a structure pointer of this type, cystic type. So we'll do stick underscore type, and then we'll just declare we'll just do cystic type and star, and say we'll do cystic base only. Okay, so we do cystic base. So what we have done here is, let's stop the debug session. What we have done here is we have declared a pointer to the structure. Now declaring a pointer to that particular structure the structure is not occupying any space here. There is no memory allocated to the structure. We have just created a structure pointer of this type. That is all we have done. We have not allocated any, and these are volatile for the same reason. That is, we have to force the program to read these registers every time. So these are volatile for the same reason as it was for the previous method one. Now basically this one, they have made it as a volatile constant because this is a constant value. The calibration value is something, it's a read-only value. That's the reason why they have made it as a volatile constant. So that's okay. So now what we need to do is, here is the trick. So now the SysTick base, whatever pointer you had created, so just have it here, a SysTick base, and then do equal to the memory location. So again, the memory location is going to be E000, E000E010. So let us do a define. I should not have deleted that line as define SysTick base, and then let's do E0x E000E010. Okay, so semicolon. So we do hash define SysTick base E000E010. Okay, so this is the SysTick base now. Now in this case, in this particular case, we do not have to write the offsets. Because the register addresses, the register locations are already mapped by the structure. You see this? This is, as we said, turn the structure over its head, and these values will map the register location, because the structure means to point at the offset 0, offset 4, offset 8, offset 12, and so on. So all we need to do now is, so when we say SysTick base equals, okay, we'll need to say SysTick base. So sorry about that. So we cannot do this. So say SysTick read write, okay, and then we do SysTick read write RW, and then this is SysTick base. So this pointer is the SysTick base. So we'll have to assign here this is SysTick RW. SysTick RW is the value, but we have to do SysTick type star, because we have to put this here. We have to typecast it, right? So this is in 2 lines. Okay. So if we needed to club these 2 lines together, we would have to do this. Okay, and then this one will go. So now we have declared a SysTick base, and then SysTick type star. This is the SysTick RW. That's the register location here. Okay. So now SysTick RW is the address, and this is already been mapped. So now to read the same location, what we need to do is different. So we need to do cystic base, okay, and put an arrow and say you need to access the control register at location 0. So that's all you need to do. So can you see how short it has become? So let us see now if we have to write 2 into that value. See, and this one again becomes this. So is it not shorter? So your representation becomes much more concise, and all of this, all these structure declarations are going to be in the header file. That's the CMSIS header file, which we are going to reuse after some modifications. So you don't have to write it. And even for method 1, whatever hash defines that we saw will be in header files. We don't have to write those hash defines, that is the base and the offset, whatever we saw. For method 1 is also something that we don't need to write. That is going to be in the header file. So I would not say that is, I would not disadvantage method 1 so much. Method 1 also has, method 1 is more precise. I would say you don't need to worry about padding and stuff like that. Here it's done through the structure. So let's try to put it on debug. Let's compile it and put it on debug. See what happens. We get some errors. So let's see what has happened. CTRL in something which is not a structure or union. So let's see. Cystic type. Conflicting type for cystic type. Oh, I'm sorry about that. This is caps. This is caps. And this is caps. Okay, so this is cystic type. This is all caps. Let's save it and let's run it again. So we have a problem here again. Conflicting types for cystic type. Error. Which line is this? 58. So cystic type. And so the mistake that I was committing was, and the reason I was getting an error was that this structure declaration I copied from the memory map header file. Okay, and the memory map header file also has the same type def struct. So obviously there would be a conflict of type of this particular structure that is declared. So let us name it something else here. So once we name it something else, this should work. Let us say cystic type. We will say it's we'll just keep it as cystic. That's all. We'll not name it anything else. Cystic. Let's hope that it compiles now. So just a moment. Why are we getting so many red lines? Okay, let's see. Let's give it for compile. We are committing some mistake. Okay, so we have 2 semicolons here. Is that the problem? Okay. Oh my god, 5 errors. So what is the problem? All right. So, no, this is also not the problem. Cystic star. All right. Let's see where the problem is. Let us debug the code. Okay. So error. Cystic base address. So we see that 150 we have. All right. So this is again conflicting with something that we have in the header file. So let's name it something unique. Cystic _ base address. So this is not this is not there, I'm sure about it. So we'll just do sysdig underscore base address and sysdig underscore. So I'm keeping this part of the video, I'm not cutting it, because you will also see what kind of mistakes can be made here. So if you declare, if you have to be certain about certain variables that you are creating, obviously the compiler is going to tell you that. The compiler messages, you will have to look through the compiler messages and see if there is a declaration of this value somewhere else, so that you are getting conflicts and so on. So as you can see, I got those conflicts. Now let's try to compile. Hopefully it will compile now. Yes. So now it compiles and it should go into the debug now. Yes. So now let's step through like before. So this is the sysdig RW address, that is a sysdig base. Or so since we have named this pointer as sysdig base, we named it as sysdig RW to avoid conflict. So now this one is going to create a pointer of type sysdig, and then it is going to assign this address to it. So this is fine. And as we discussed, the pointer is going to be just the structure pointer is going to look at this address location as the structure only. So it doesn't care whether it's some peripheral register or memory location. It is going to look at it as this structure. So let's go forward. So we have sysdig base CTRL. So here we get the value of 0 again. So that doesn't tell us anything, but I'm just keeping it. Now we will write a value of 2 in here. So as you can see, the value of 2 has come, but we are doing it in an entirely different way from method 1. But the final result is the same. So we have 2 here, and then we'll write this value back into the variable. So let's do this. So the variable value is 2 now. So these two methods look pretty different, but they are doing the same thing in the back end. Okay. So, and we will be following method 2, and we'll follow method 2 because, as I said, we are going to have the memory map file that we have for is the CMSIS header. It's a part of the CMSIS header file. We made some, as I said, there are certain changes that I have made, but the structure goes this way only. So we'll also have a look at this file maybe after this. Okay, so let us do a few more things here, and then we'll have a look at this file, that is what it comprises of, that is the memory map file. So let us now go into this, and suppose we want to access the load register. Okay, so this is the reload value for the sysdig. So this is a writable register. So let us change the values to load here, not val. So load and load. So we are accessing the sysdig reload value. So let's not bother about what the reload value does and everything. We will look at it later. We are just manipulating this register value now. Now let's look at the sysdig reload value register. This is the register where you load a 24-bit value for the sysdig register timeout. Okay. And we will also use this register for our bitwise operators, because this register is a good candidate to do that. Okay, because this is not this has got quite a few bit fields which we can manipulate. Anyway, so let us compile the code and see what we get. So load means we are in the offset 0x04. So this is offset 4. So let us put it for debug first. So now once we've put it for debug, let's go into the memory view and let us add a watch in 0x14, which is the reload value register. And so this is where your reload value is. Now what we do is we single step. So this is assigning the SysTick base address here as usual. Now we'll see that, and for the load value register we can load bigger values. So we can load up to, say, for 24-bit all ones. So 46 to 24 FFF we can load in the load value register. So yeah, you can do that. 24 bits, right? Yeah, 466. Yes. All right. So let's step through. So let's see what value 1 is. So value 1 will be nothing now because we have not loaded anything. Here this should change. So let's keep an eye on this. And of course, the value has changed to ABCD. ABCD. CD is in the lower bit and AB is in the higher bit. Now, why ABCD comes like this is because this is a little endian architecture. Okay, so let's talk a little bit about that. So our register location is E000 E014. So it goes like this. So this is the register that we saw, and it's say, so if so addresses of anyway bytes, so E000 E014, this is E015, I mean E000 E015, this is E000 E016, and this is E000 E017. Okay, I'm just putting 17 for as a shortcut. Now for little endian, what basically happens is ABCD is the number. ABCD is the number, and it starts from here. So since CD is the lower byte, okay, CD comes here and AB comes here. This is little endian format. Okay, so that is why you are getting it this way. Now if you go to the memory browser now, so you can see the same thing through the memory browser. So let's put the same address location here, 0x E000 E014. Okay, and you see 0000 ABCD. Now you see it straight away. So here E014, and the address goes up higher like this, 014, 15, 16, 17. But this looks different from this. Here it says byte 0 has CD and byte 1 has AB. But if you look at this, don't get confused here. Here byte 0, that is E014, should have CD, and this byte should have AB. See the addresses here, E14 and 15. But the display here, the memory view is as per you. This is for your convenience. The display is per your convenience. If you right click and look at the endian, you have opted for little endian, and that is why it is showing you this way. It is not faithful to the byte addressing here, but this is showing it for your convenience, because if you choose big endian, you'll see that the number reverses. Okay, CDAB 0000, and it looks as if with the increasing address you see the right number, but actually what is happening is if you choose little endian, you'll see the number as it is. This is for your convenience, and this is the actual format. Okay, so now let's go further. Let's single step and see what's happening. Of course, again, and then the value 43981 has come. So let's see what the hex value is for this number format. Let's see hex, and you'll see ABCD has come here in the value 1 register. So we have learned both method 1 and method 2. I mean These methods are named by me. These are not standard methods. You won't find method 1 and method 2 anywhere like mentioned as a standard method. I call it method 1 and method 2 for my convenience. So we are going to use method 2 and hope you understand how method 2 works, and it is easier to express, and that is why. But at the background, more work goes in, because you have to declare these structures and you have to ensure that these structures are properly aligned and so on, which is already done by the memory STM32 memory map. All we need to do is to I have separately mentioned this register here, but we don't need to do that. We will only have to access the registers or access the values that are mentioned in memory map STM32F4, and we'll call the values and we'll do. For example, let's have a look at this particular file, core initialization STM32F4.c. All these things, all these accesses that you see, flash, ACR, they are all from that header file. We have not written anything here. That is, we have not written the map here. All these maps are coming from this memory map file. So you don't need to worry about it. This is for your understanding as to how to go about doing this. So this ends this lesson on method 2. In the next lesson, we will see how structure padding could confuse the memory read and write. That is, if you do not, so all these structures are properly, the layout of these structures are absolutely fine here. The MCD application team has taken care of everything, alignment issues and all that. But in case you are declaring a structure to access some memory location without the help of that header file, then you might face some problems, and we are going to discuss about that in the next lesson.